answer like they always do. A new type of sensor to get us through. Oh, Mama, when will we go back to school? 'Cause I wanna become a researcher too.
So welcome everybody again at this fourth and last episode before summer of our online talk show on science, technology, society. And tonight we will focus on the medical research that's being done at our university around the virus. In the studio, Sonja. Welcome, Sonja Garcia Blanco. Nanotechnologist developing an amazing technique to detect the virus in an optical way. But there's more science tonight. There's Dilu Matthew from the UT company Easy Sense, and he also built a sensor which works in a different way, which can also detect the virus. So what are the differences? How do the sensors work? Now we have a student technical medicine, Jorrit van Poelgeest, who worked on a ventilation mask and helped to improve how we can treat patients with the virus. And Maarten van Aalst, actually on video, with a short talk about what we can learn from the virus to deal with other disasters maybe that might affect our society. Don't forget, you can always ask a question via the chat. They will arrive here at the table and I can ask the question on behalf of you to the guests here in the studio. But first, we'll talk to you, Sonja. So you're an expert in the field of optical sensors. You've done a lot of work already on sensors to detect biomarkers for cancer in urine, for instance. Diabetes sensors. So now you are working on the coronavirus. How did you get the idea to suddenly start working on this?
Yeah, that's a very nice question. Thank you. Actually, it was a coincidence. I was trying to get used to this lockdown. And so I was working from home, and somehow I got a call for this proposal from the EU, Horizon 2020, that was about research for corona. And one of the topics that they were asking was for sensors. So I was like, oh my God, maybe we can use our sensors. So I checked the call. Oh, the deadline is in 5 days.
Incredible.
So I was like, oh no.
Welcome to the world of a scientist.
Yeah. And then I was like, okay. So I called the consortium because we have been working for 4 years in this GLAM sensor, which detects cancer biomarkers. So it's also an optical sensor. And we thought, okay, we have the consortium. So let's just try to submit.
Yes.
So we worked the whole weekend and we submitted.
Amazing.
Unfortunately, it didn't get granted.
Oh no! Welcome again to the world of a scientist.
It was like only 8% chance of success,
Wow.
and we were in the provision list. So we were like the next couple of proposals that didn't get granted. But Mesa Plus said, "Oh, but this is very interesting. Why don't you start working on that?" So they gave us a small budget, so that we can continue advancing in developing this sensor, and then we don't need to catch up. So we're already going.
Amazing.
So meanwhile,
Amazing.
I'm looking for more funding opportunities, of course.
Wow.
But,
So can you explain to us a bit about how it works? There is actually an artist impression of your sensor. Maybe we can
so
see
we
it
can
so
look
that
at
you can
the...
explain it. Yes.
So there you can see the optical sensor. So it's microfabricated, so it's made in our Mesa Plus Nanolab. And you can see that there are several channels. So the red arrows represent the laser light that is coming into the sensor. And then there are some circles that are ring resonators. So on top of these circles, we can immobilize some capture probes that capture either the virus or the antibodies of the virus or some other proteins that are called cytokines. In particular, we're interested in the IL-6. And they can get immobilized in the surface of the sensor, and then the ring response will vary. So we have different variations of this ring, but this is what happens.
Incredible. So you're actually not looking for the virus only, but there are other markers that show the presence of the virus. That's
exactly.
How we should see.
So the idea was basically to put a drop of blood or blood serum in the sensor, and then see, okay, do you have the virus? Do you have the antibodies? and other markers that could detect, you need to have this treatment or this other treatment.
Yes. So does that mean that you could actually, using your technique, if it would work in the end, that you can also use it to show that you have had the virus, but that you have recovered?
Exactly. Like if you have the antibodies, means that you have had the virus. So if you don't have the virus, but you have the antibodies, you don't show that you are immunized, but you show that you had had it.
Exactly.
And then if you have the virus and you have a certain amount of the other biomarker, then the doctors could probably select a better path for your treatment.
Are the biomarkers that you're looking for with your technique then somehow comparable to the biomarkers for cancer or for diabetes, or is it completely different?
Yeah, the thing is that the optical sensor detects changes in refractive index. So anything that changes the refractive index then can get detected. Okay. So what gives the selectivity is the biolayer that you put on top.
Okay.
So for the cancer biomarkers, we put some capture probes to detect the protein that we want to detect.
So that means that one specific from protein has one specific kind of refraction index?
No, depending on the size. What is the capture probe is specific. So for example, you have this protein, you have the antibody for the protein. So if you put the antibodies on the surface of the sensor, this protein goes and only that protein attaches to the antibody.
Okay.
So then that produces a change in refractive index.
Yes. That's okay. Okay. So I mean, if people hear an optical sensor, then people think a camera.
No,
but of course, this is not. This is not that you make a picture. It's actually more that you can show the presence of specific particles.
Exactly.
Using a specific sensor.
Exactly. So that's why we can multiplex. We can have different channels, and in each channel we can put a different capture probe. Okay. So now we want to detect the virus, the antibodies, and the IL-6. But if the doctor say, it's very interesting to detect this other particle, then we can just say, okay, so give us the antibody, we put it on the surface, and then it will also work.
Blood is what you need to do the test, right? But does it also work on what you spit out, on your mucus, or on other?
Yeah. The thing is that, of course, the sample needs to go through a microfluidic channel to reach the sensor. So if you can prepare it in that form, it's okay. Yeah. And then also there are other nasty things in the sample that is not only the molecule that you want to detect. So provided that those nasty things don't attach to the sensor and make bigger change than the protein that you want to detect, then you can measure.
Yeah, because that's indeed another question, of course. How specific is it? Is it a reliable test, or do you have many false positives, or maybe do you miss a lot of patients?
We're not yet there. We have not yet analyzed that. But as I said, the specificity is given by, first we have an antifouling layer that nothing should attach, apart from the ones that attach to the capture probes that you do voluntarily. Yeah. So you attach these capture probes, and then everywhere else nothing should attach. Yeah. So that's what gives the selectivity. So
blood, of course, is not the easiest way to test someone, right? So if you would like to test it, or if you would like to test someone before entering the plane or something, it might not be feasible. Or could you imagine a nano needle just taking a little bit of blood without you even noticing it and then testing it, or is that science fiction?
I don't think it's science fiction, but of course, full blood, you need to prepare somehow. So but it's not science fiction. You can filter it through a little microfluidic filter and then bring it to the sensor. Of course, the saliva or the urine are less invasive. Yeah. So then depends where the things that you want to detect are.
And also there you could detect the virus. Also in urine you could detect virus antibodies.
If they are present in that medium, yes. Wow. Like with the GLAM sensor, we detected the cancer biomarkers from urine.
Yeah. Wow. So how far are you? Is this just a lab test now, and does it take a lot of time to scale up, or are you almost ready to do this at a larger scale?
It is still in the lab, of course. So we are first testing that we can actually detect what we want to detect. And at the same time, in this little project, we're working on a module so that we are working in parallel to the module that you can insert the sample and on the sample. And the sample at the moment, we characterize it with a big setup in the lab. So when the two parts are ready, we make them converge. And hopefully by then we have more funding.
Yeah.
Because,
It is amazing. I mean, the virus emerged just a few months ago. The lockdown started like 3.5 months ago or something. And now we are already here. I mean, people often say that in business people are fast, but in science we're always so slow. It's amazing. Yeah?
It's really a great motivator. I think you can do something for society.
Yeah, amazing. Wonderful. So, well, I really hope that you can scale up soon. Let's talk about another method that's currently being developed also almost at the University of Twente. It's a spin-off of the University of Twente, Easy Sense. Dilu Matthew is online actually here, and together with somebody else in the company, Pepijn Beekman, he's also working on a sensor to detect the virus, but the sensor works in a different way. So welcome, Dilu. Wonderful that you're here online. Of course, it would have been great if you could have been here live in studio, but the 1.5 meter doesn't allow us. So it's wonderful that you're here still online. So before we talk about your method of how you make the sensors, let's first take a look at a short video where you were at work in the Nano Lab at the UT. It was shot in February, and there actually we see you together with the other person in your company, Pepijn, in a pre-1.5 meter setting. So this is an old recording, mind you. So can you explain us what we see, Dilu?
Yeah. We use a wafer from the mask. After the development, these relatively coarse patterns are used to define the electrical contact paths for measurements later on. And later we use electron beam lithography that helps to pattern the nanometer-sized electrodes, which makes this sensor extremely sensitive.
Wow. Fantastic. Really nice to see. I mean, this is all just at our own university here. So around the corner is always so amazing to see that. So can you explain, how does your technique work exactly? How do you detect the virus with your technique?
Yeah. Before I explain how our technique works, I would like to say why our technique is better, or why our technique is unique.
We got competition here.
That more than 50% of the times the spread of the disease happens even before the symptoms are shown in the patients. This is very important because people doesn't know that they're infected. They go out as a normal person while they're unknowingly infecting other people. So how can we stop this? How can we prevent this? So you have to have an early diagnostic test and do a mass screening to prevent this. But unfortunately, none of the current existing technologies or testing methods are capable of doing this in early diagnostics in a reliable way. So that's where we are unique, and we are very important as well. So we do digital sensing, which means that we detect individual viruses. So we count the viruses one by one. So you can imagine that if there is one virus in a sample, the person is already infected. So since we can count these particles, we can do it in a very early stage. So that's how we are different, or we are unique from the other existing technologies. On top of this, we have an active method that brings these viruses to the sensor surface, which makes our sensor extremely fast. Like in a 1 or 2 minutes, we can make the test. So that makes the whole sensing technology rapid. And on top of that, we also have another advantage, which can detect or distinguish the specific binding of the virus to the sensor and the non-specific another particle which is in the sample. So this is very important, because then we can have a better selectivity. At the end, this gives the better reliable test results. So combination of rapid sensing, more reliable testing, and counting the particles one by one gives us the edge over the existing technologies.
Wow.
This is not the end, so I can go on saying more and more. If you,
I have more questions.
Label free, calibration free, real-time measurements. It goes on, but I think this is enough for the.
Incredible.
For this
discussion. Let's talk in a few minutes a bit more about the application of it. But now I just want to understand how it works. So. What does your sensor detect in a different way than Sonja's sensor? Do you detect other particles? Is the technology different? I mean, this is not an optical technique in your case, right?
It's not. The main difference is that Sonja does the optical method and we do the electrochemical method. Both techniques are already available in the market. So, for instance, glucose sensors are based on electrical sensing, and most of the other sensors are optical testing. So, both of these techniques are not new. But as I said, the main difference is the digital sensing that we have. So we count the particles individually. I presume that Sonja's sensors would depend on a few particles at least to bind to get a change in signal that is recognizable by the sensor to give a meaningful difference between a noise and the signal. So that's a main difference.
Okay, so this is a lab on a chip, right? This is
lab on a chip.
Yeah. So
you can imagine like a box, like a shoe box, with all the electronics, and where you have a small cartridge which you hook onto the shoe box and put the sample on top, and you can measure it. Yeah. So this is highly portable. You can do it at anywhere you want to.
And what you detect is the virus, not antibodies. Or so you detect the virus particles, and you can count even how many of them are.
Yeah, so there are different focus fields, of course, but we are focusing on seeing whether the patient is currently infected or not. So for that, we do the virus detection, but we are not just bound to that alone. We can also do the antibody testing. In the future, we plan for that, but at least in the beginning, we focus on this because this is the need of the hour.
So how do you know that you see the virus and not something else? So we just heard an analysis of the refraction index and how that changes when the virus attached to an antibody, etc. So what's your trick? How do you catch the virus?
Yeah, so it's again the antibody binding to the virus. Yeah, that's a biochemistry. That's the same. We are not reinventing the wheel. It's the same thing. Okay. So the specificity is the way. But on top of that, we have method which is derived from the measuring technique that we can see whether this is a specific binding or a non-specific binding. Yes. That gives us an edge over the current methods.
And being able to count the number of virus particles, is that important? I mean, does it indicate somehow how far people are in their infection? Or
that could also be, but the important. So if you think about that, we are going to put our testing device in the airport or at the entrance of a festival or stadium. So people doesn't want to really know which stage they are at, or they want to know whether they have the infection or not.
Okay.
So the most important part is that whether the patient is currently infected or not. But of course, we can do a quantitative analysis to see how far or how many viruses per sample we could do. Yeah.
So the most important thing for you probably is that you can already detect the virus before you have the symptoms, which is the dangerous thing of this virus, that we can already spread the virus before we even know that we are infected, right? And that's why you believe your technology can help, right? So I also heard you say that within 1 or 2 minutes, and you spoke about 10 minutes. Why is your technology so fast?
Yeah, I also mentioned this in the beginning. So we have an active method that brings the virus or the particles onto the sensor surface.
Exactly.
That's this improves the speed a lot. Other sensors have to depend on the diffusion and the microfluidics based on.
So Sonja could use that method as well.
Mm-hmm.
No?
Yeah.
Yeah.
In principle.
Okay. Yeah. Okay. So then you could also go for the 1 minute test. Interesting.
Unfortunately, this is inherent for the electrochemical measurement technique. Okay. So if she wants to shift to electrochemical, probably she could.
Maybe we can find a nice hybrid. Hey, so how far are you? I mean, are you already ready to scale up? I mean, you are a spin-off company, so maybe you're even faster than Sonja's research is going.
Yeah, true. So we have already in the clinical proof of concept of the technology. We are in collaboration with Spectrum Twente Hospital, and also their microbiology lab called the Lab MICTA. So they are already collecting samples for us, which should be tested and validated against the gold standard PCR technique at the moment. In the next few months, we will do that. In parallel, we are also talking with big partners. I don't want to name them here, who could scale up the technology for us as fast as they could. But of course, we also have to take the certifications and at least emergency use only label. It takes a while, like 6 to 9 months from now. We think that our technology could hit the market.
Interesting. Okay, so there is a question actually from the audience for both of you. And the question is, you both actually need, in the end, a form of approval of the RIVM, the Dutch, how do you call that in English? The Dutch Institute for Public Health, I think so. Are you working on that already, Sonja? Or is it too early for you?
For us, it's still too early. Yeah, because first we need to still demonstrate the whole technology.
Would it be difficult to get that approval? Do you have any idea how that works?
To be honest, I don't know how difficult it will be.
No. That's for later.
Yeah, that's for later.
Are you working on that already for your test?
Yeah, we are trying to involve key opinion leaders in our project because as a company, this is very important for us. But this is very in the early phase, so I cannot reveal anything at this moment. But hopefully, by the time our device is ready, we have an approval from IIM as well.
So, what is the most important thing to get that approval? It must be something about the specificity and the selectivity, maybe that you don't have false positives, but that you also don't miss too many people.
We have to see that there is no false positives or false negatives, at least compared to the golden standards out there like PCR techniques or other antibody testing. So first, during this phase, the clinical proof of concept phase, we validate this against the existing methods.
Okay.
Yeah, it's a lot of bureaucratic paperwork where you get the approval from EMA and FDA, and also for CE certifications.
Yeah, of course. You don't want to limit yourself to this country only.
Of course.
You want to conquer the world. Which I can imagine.
It's a pandemic, right? It's not just limited to Netherlands.
Not a Dutch-emic.
Help the people everywhere.
Yeah, exactly.
Yeah.
Okay. Let's do a little peer review here. We just heard how hard it is to get funding. Well, we have two academics who can evaluate each other's work. So yeah, what do you think? I mean, is this a good way to do it? What can this method do better maybe than your method? And is there something maybe that your method could do better than this method? Or is it not comparable in that sense?
I think both methods are really interesting, so I will not say one is better than the other. But what I find very interesting is how fast Dilu's method is, because when you need to test so many people, I think every minute counts.
Yeah.
So then you can really do a lot of tests, really massive screening of the population.
Yeah.
Also, maybe the cost, we didn't talk about the cost, but I imagine his chips maybe are a little bit cheaper than ours. So then, in our case, we are also doing the multiplexing. So that means that we can get more information from a single measurement. So that could also have some advantages.
Yeah.
And another advantage of the optical sensors is that they are immune to electromagnetic interference. So that is very interesting because if you are working in an environment where there is a lot of electromagnetic signals, then our sensors don't notice that.
Yeah. So an airport would actually be better for your technology.
Maybe, that needs to be, probably that makes the module, maybe that just needs to be shielded or something. Yeah. But in our case, comes naturally.
And in terms of the accuracy, do you think, so in terms of the specificity and the selectivity?
I think in that our method is also quite sensitive and selective. We have not done massive studies yet about specificity, because we target this, what is the limit of detection, but we have already proven for the proteins for the cancer that 300 picomolar in urine. So in urine there is a lot of nasty things, and still we had a very nice limit of detection. Yeah. And the virus are much bigger. Yeah. So that changes more the refractive index. So should be even able to detect lower concentrations. So we are quite positive that it will have very good limits.
Interesting to hear. So, what do you think, Didu? What are the main differences, maybe, and in terms of the specificity and the selectivity, or the other aspects?
As I said, I believe that we have higher selectivity and sensitivity, but that doesn't mean that Sonia could do better. Of course, we are not in a competition here, so I hope both technologies will eventually hit the market. But one remark that about the electromagnetic interference, it can just be avoided by putting anything in a box. Just a small box can completely avoid this thing. So that is not a problem for us, at least. But one of the important or the easiest thing for us is the scalability. The semiconductor industry has advanced a lot, so you can see that immediately touching your pockets and see your smartphone. Whereas the optical techniques is not as advanced as the semiconductor industry. So scaling up could be a challenge for Sonia, whereas scaling up is much easier, at least for us, based on the existing semiconductor industry.
Yeah. Interesting. I mean, it's the difference that I picked up from the first talk that I had with you, Sonia, is that you can also, with your technology, detect if somebody has been infected but does not have the virus anymore, but still has antibodies, right? That seems to be a difference, right? Because your technology detects the virus itself, and when you're cured, then the virus has gone.
No, in principle, we could do that as well, but based on the business model, at least we focus on the early diagnosis. So there are three ways. Early diagnosis, you can do that, or you can see whether a patient could develop severe symptoms based on some markers. That is the second thing. And the third thing is whether the patient already had the virus or immune to the virus. So these are the three things, but we focus initially on the first one, but later we could extend to the later. Parts as well.
And I just wanted to make a remark about the scalability, because I do not agree that the optical sensors cannot be scaled up, because they're also using microfabrication technology. So we fabricate our sensors in the clean room, we do lithography, etching, and...
What I meant is the limitation of the optical detection platform, but this is not not a point of argument or anything. I just passing by remark. Yeah.
But could we also maybe anticipate that your technology, Sonia, would maybe be more applied in hospitals? Because my impression is that it's a bit more solid, and I don't know if it's more accurate, but it sounds like there are many ways in which you can detect the virus, antibodies, other elements, and the lab-on-a-chip technology seems to be very suitable for large scale, and for pop events, for entering the train and checking if you're infected or not. And so that might be also two totally different fields of application. Is that a good intuition, or am I totally missing?
Yeah, of course. As Sonia said, if they want to integrate and give more information about the disease, then that's what she could do. But at least for the time being, we focus more on the fast, reliable diagnosis of the disease.
Maybe it's also good then to move a bit to the societal implications. We've been discussing a lot of technology. It's fascinating stuff. What you often hear as a worry from society is that the pressure that you feel as a scientist to come up with your results fast can also sometimes be a seduction to do somehow sloppy science. Do you feel a pressure, and what do you do to make sure that you stay being very accurate and very integer in your work? Do you feel that, Sonia, that there is a pressure to go fast? Yeah,
it's a pressure. I don't know if it's from society or from ourselves, because we really want our sensor to work and to detect and help, but still we're doing the things in a proper way, scientific way.
Yeah. That's maybe also
and
why
also,
it takes...
I think we don't have so much pressure as maybe DILU because we are at the university.
Yeah.
So, okay, we're doing the things, yeah. So I imagine DILU must feel much more pressure because it's not only the pressure from society, but also of the company that now is the opportunity.
Yeah. True, but we also feel the societal pressure as well. So when everybody was locked down and sitting at home, we felt like doing nothing and good for anything. So that's a time where we thought about changing our plans for cancer diagnostics and move to COVID-19 detection.
Wow.
So I think it has a high impact because every day you hear thousands dying in the world and hundreds of thousands getting infected, and nothing is as usual anymore. You can't travel properly, nothing is open as usual. So that gives a societal pressure as well, definitely. Also, as you said, business-wise, we also have a pressure, or we are in a race because you can see that many companies are on board of COVID detection, so we are also running there. Yeah. So pressure from both society and business as well. True.
So how then does it affect your earlier work on cancer? I mean, that's also quite important, I would say. And many more people are still dying of cancer than of COVID-19. Of course, I don't want to say that we are not in a very serious situation, but do you learn something from all this work for your cancer research, or is it just postponement? Yeah,
I think it was a really great opportunity because somehow make us focus on really pushing forward the technology. So we had the opportunities to create a little team that now is working really fast. And then all the technology that we will develop now in this coming 3 or 4 months can be used also for the cancer detection. We can just change the capture probes and the different antibody protein pair, and then we detect other biomarkers. But everything else stays the same. The module will be the same. The chips will be the same. So it's really accelerating also for other diseases. Of any disease, cancer, diabetes,
Interesting. So we should not really see this as a pause in your research.
No. It's an acceleration in the research, I think.
Wonderful. Is it the same for you, Dilu? Or are
exactly
you
the same.
Okay.
Exactly the same for us as well. So the platform technology is the same. The handling of devices, everything is same. The shoebox that I mentioned with the electronics is the same. So basically all the certifications and everything that we get is mostly the same as well. Only thing is that the antibody interactions changes, so you have to do a clinical validation again for the cancer. But that is much easier compared to what we are doing at the moment.
Okay, wow. Fascinating. It was very nice to hear you, Dilu. Thank you so much for telling us about your work. I really hope that you will succeed fast, and I hope that for you, of course, as well.
Yeah.
So thank you for being with us.
Yeah, my pleasure. I liked it. Yeah, thank you very much. Bye-bye.
Bye-bye. So, of course, it's not only scientists, entrepreneurs who help us to somehow exit the situation regarding the virus, but also students, obviously, are very active in this respect. So we're now going to watch an item that we have recorded a few days ago about one of our students, Jorrit van Poelgeest, a student in medicine, technical medicine, who helped developing a ventilation mask. So we're really very happy to announce that Student Report made this item. They actually joined our team to make these talk shows, and they actually make monthly videos on student-related topics. So now we switch over to Samar Kamal in the Tech Med Center.
Thank you, Peter. Hello, everyone. This is Samar from Student Report Live. It's interesting actually to know about the medical work that's going around the university, and it's more interesting to know about Jorrit, who's a student doing technical medicine masters, and he's also participating in one of the corona-related researches. We want to know how he overcame all the challenges, especially that he have to keep both physical and social distance. So let's talk to him.
My name is Jorrit. I just turned 24 years, and I'm a second-year master technical medicine student.
Could you tell us how did you get into the research?
Sure. So I wasn't allowed to join my internship in the hospital anymore because of the coronavirus. So I wanted to be helpful and sent an email to one of my supervisors of my internship, and a few days later I just joined his research team here in the university.
Tell us a bit about the research you are working on.
The research we are conducting is about the coronavirus. The coronavirus affects the lungs. Ventilation systems that provide continuous pressure can be beneficial for patients because they keep open the alveoli of the lungs, the little air sacs. So, however, the normal ventilation systems disperse the virus because their exhaled air just flows in the environment. So what we did is we are testing and designing systems that keep the benefits of ventilation systems to provide continuous pressure, but also not dispersing the virus.
What are the strangest things you encountered so far in the research?
The strangest things, well, one weird thing was we wanted to measure the volume of our front face. So therefore we just filled up a bucket to the brim with water and we had to put our face in, and logically the volume of our face was pushed out. So we had to push our faces in buckets of water.
What kind of difficulties you're facing, if there is any?
Difficulties, well, it was difficult to keep up with the corona regulations. At some point we had to do emergency removal tests of the ventilation systems, and at that point we just couldn't keep distance.
Do you have any advice for students who are sitting at home wanting to help?
Just be proactive. Dare to send an email to anyone you know in the medical field or research field offering your help and see where you can be helpful. However, ironically, just sitting home is already helping.
Well, that was it. But at least now we know that if you're interested to participate in a corona-related research, you could do so. But did you know that by donating blood, you also participate in a group immunity research? That was all, everyone. Thank you for watching. And now let's go back to the studio.
Wow. So students putting their face in the water to make a ventilation. Well, I normally ask my kids to do that when they have a party. Amazing. So what do you do? Do you also do things with your own students to somehow stimulate them to do work in relation to the virus?
I think they're already very self-motivated students, so I'm very, very lucky.
Amazing. I mean, this is really so amazing. I mean, if anyone still dares to say that science is slow, sometimes it's good to have slow science to do it in a good and a solid way. But I mean, the way in which many people now jump on it and come with very fascinating,
if somebody says that, they should come to the lab.
Exactly. Amazing. Well, it's really very nice to see that also that the University of Twente, I think, offers so many possibilities to their students. So wonderful. So do you think that this is an important, well, I'm actually not sure if it's in your field, but do you think that this could help? Is this an important contribution to the ways in which we could help people who are infected with the virus?
Of course. I think every contribution is very helpful.
Yes, exactly. It sounds really interesting. So a way to help people, with a ventilation system that does not so much spread the virus. Fascinating.
Yeah.
Wonderful. We have actually another pre-recorded item on a different topic, also related. Maarten van Alst, ITC professor, director of the Red Cross Center for Climate. He will explain actually the effects of the lockdown on our environment. And he's a specialist in, risks, and actually, especially in risks that add up to each other. So when one disaster follows the other, how that affects our society. And we actually asked him the question that a French philosopher, Latour, has asked our society. Is the crisis that we are in now a dress rehearsal for maybe a much worse crisis regarding the environment? So, is that true? Let's watch the video.
Thanks, Peter Paul. Intriguing questions indeed. And of course, as an international organization, the Red Cross is coping with the COVID crisis worldwide. The direct health impacts are, of course, terrible, but also the indirect economic effects are huge because of all the lockdowns around the world. And we're getting the question often if that's good news for climate change. And indeed, we are getting much less emissions this period. Economic activity is suppressed. Of course, everyone's aware transport has halted, at least international transport, planes and all of that. But it's still only a small decrease in carbon emissions. So if you look at an analogy of a bathtub that's being filled gradually with increasing greenhouse gases, we've now turned the tap slightly lower, but overall the bath is still filling up. And we're still, in terms of the climate crisis, approaching the moment that that bath is going to spill over. So we should still be concerned. And of course, the big question is also what's going to happen when the lockdowns end? Are we just going to turn the tap full open again, or are we going to be doing it differently? At the same time, the real challenge is that indirect economic effect. So we are most concerned about the most vulnerable groups everywhere in our societies here, like in the Netherlands, but also especially around the world, and most so in the poorest developing countries, where people already have low coping capacity and are now hit doubly hard by these indirect impacts of COVID, but often compounded by a range of other challenges. And they may be other economic challenges, but also especially those climate challenges. We've already faced several cases of evacuations for major storms. We had one, Harold, in the Pacific, Amphan in India and Bangladesh, where we now have to evacuate people to shelters in times of social distancing. So how do you actually do that? You can't accommodate as many people. You need to move people to a wider range of shelters. We need to have protective materials available. We've succeeded with that in a couple of cases, but it only increases the challenge of dealing with the extreme events that are already getting worse in a changing climate anyhow. So then coming to your question of Bruno Latour, is this a rehearsal for the climate crisis? Indeed, what I see the indirect economic effects of COVID being is like the sort of shock that we will see many more of. And COVID in that sense provides a sort of X-ray of our vulnerability around the world to such massive shocks. And we're going to be seeing more of those shocks in the future. And maybe the opportunity is also then to look at how do we cope with this current shock? Where do we see the gaps in our ability to deal with shocks? In a way, those are the places where organizations like the Red Cross then need to step in to help people in the most dire need. We should be building systems that don't create that dire need and that make us more resilient for all those climate shocks that are coming our way in the future. And I'm curious actually, in terms of your experience in the lockdown, Peter Paul and other studio guests, what are you doing differently? What have you learned in the lockdown? And is it going to be back to business for you now that COVID is retreating? Or are you also changing your own behavior and your own practices going forward?
Wow. Thank you, Maarten, for this impressive analysis. Maybe it's not the most happy end of our 4 episodes, but an important one. If it's a rehearsal, it better be a good one so that we do better next time. So, what would be your answer? Do you intend to change central things in your life now that we've been in this crisis?
I think the crisis has really taught us a lot of things. For example, we don't need to maybe travel so often to meet other people, to have regular meetings. We don't need to do international travel maybe, not all the time. We can do a lot via internet. And yeah, so those things I think is easy to implement. Hopefully we can keep that going. And also that you can relatively easy work 1 day, 2 days at home. And that also reduces a lot of commuting. If everybody does that, it's a lot of commuting that gets saved in the world. Yeah.
Beautiful.
So
yeah.
because the world is going to continue even if, So we need to make sure we are here to enjoy it.
Do you think our world will still exist in the year 2100?
I hope so.
Maybe that's the only realistic answer that we can give.
We need to think about our kids and our grandkids and just keep the world.
Well, that's indeed why I like the metaphor of a dress rehearsal, in the sense that if it doesn't work well, we could change things. And what I really learned myself, I think, is that the whole theme of vulnerability is maybe also an underestimated theme. And maybe people often see technology as the solution. We have the power to do everything. And now we actually see that technology doesn't free us from our vulnerability, and that we need maybe also to find ways to deal with that, and to maybe develop more forms of resilience than to have the fantasy that we can do it all.
Yeah, and to be prepared.
Yeah. And the travel, of course, is a very central ingredient of our academic life. It must be hard to cut down on it, I think. I mean, the first month I thought, of course, why would we? But now, having been in the situation for a few months, you also start to miss the real interaction with people.
Yeah, that's why I say not all the time, but you can reduce a lot.
Yeah, exactly. Well, let's see. Let's hope that we will emerge from the crisis in a better way, and maybe also that after summer we will have emerged a little bit, and that we can go back to campus a little bit more often. And especially really we can offer our students a bit of teaching again. And that's the firm intention of the University of Twente. And the whole idea of the 1.5 square kilometer campus is a nice idea. I think that's what we can give our students. So I really hope. And then this was our last episode before summer. We are not entirely sure if we will return after summer, but maybe we hope so. And maybe you could even expand the scope of our episodes a little bit, maybe not only focusing on the virus, depending of course on the situation of the world, maybe focusing a bit more on science, technology and society. Let's see. Stay tuned. Check out our website. We will also let you know via social media. For now, thank you, Sonja, for being with us. Thank you for the entire team who you do not see at home here, who have been working like hell to make possible all these episodes, to do all the way. You cannot imagine how much work it is. Luc van Eerwijk for the beautiful visuals that you see, beautiful movies everywhere. Thank you so much. I wish you all a very nice summer holiday, and I really hope to see you all back. Bye-bye.